who will tell us about dimensional deconstruction and physics in theory space.
A big thanks for the organizers for inviting me. It's, oh, what do I do here? Oh, I use the other one. Oh, naturally. Thank you. You regret inviting me now. It's wonderful to be in Cambridge for the first time for me as well, so thank you. I'm going to talk about some work, basically reviewing some things I've been thinking about for the past year or so. And the primary motivation for thinking about this was to was the following very simple basic observation that, at least from the point of view of model building, we've been using higher dimensions for a while now to do interesting things, build extensions of the standard model. And there are two ingredients that they offer that make them interesting. One of them is that you get bigger local symmetries, higher dimensional local symmetries. So you get higher dimensional gauge symmetries or higher dimensional general covariance. And the other one is that locality in the extra dimension serves as a tool to suppress unwanted interactions in your theory. If you have fields that are localized at opposite ends of the world, for example, then unknown short distance physics can't give arbitrarily large contact interactions between them. They have to be exponentially suppressed by by the fundamental mass scale times the distance between them, and that's a useful thing. But the simple observation is that neither one of these things have anything to do with extra dimensions and can in fact be obtained in completely four-dimensional theories, which actually generalize in interesting ways both the idea of higher dimensional gauge symmetry and locality in ways that are often more fruitful. And so this sort of, what exemplifies this in a very simple way is to imagine that you have a four-dimensional quiver or mousse model. And so you just have a whole bunch of gauge sectors, and they're connected by fields which transform in this simple example like bifundamentals under all the gauge groups. Now let's see how this, how these two ingredients manifest. They manifest themselves in very obvious ways. Obviously there's a big gauge symmetry. There's many gauge groups. And locality is also obvious in this picture. For example, let's say I take this, this chain and I choose to shut off one of the gauge couplings. Let's say that one. Then what happens is the chain just falls apart into two different chains that cannot possibly interact with each other. The only interactions came through that gauge coupling. And so what that means is that if I have some set of operators made out of things here and some set of operators made out of things there, that any interaction between them, again, must be exponentially suppressed. It has to either go through a large product of gauge couplings, because if I send either one of them to zero, nothing can happen. Or, for example, it can go through the vevs of these fields over some mass scale, again, to the nth power, also parametrically and exponential suppression in the distance between them now on the chain. And so this simple point motivates us to think about just very general theories, four-dimensional gauge theories with a site and link structure. And for essentially the rest of the talk, I'm just going to be talking about field theories, except for a comment at the end about gravity. And in fact, I'm not even going to restrict myself in general to thinking about link fields that are bifundamentals. So there's just some very general structure which instead of calling quivers or mousses, we just call more generally theory spaces. Okay. Now, in some cases, theory spaces can look just like extra dimensions. That happens when the link fields are in a Higgs phase that tries to Higgs the gauge groups that it touches down to the diagonal subgroup. So here's a simple example. Let's just go back to that chain and imagine that these link fields are scalar fields that now get a vev proportional to the identity. Let's say this is some SUK gauge group. they get a value proportional to the identity, so there's some Goldstone boson field U. So at low energies, I have exactly the same picture again now with these Goldstone boson fields being the connecting link fields. The Goldstone boson fields, there's some e to the I pi, or the pi are the canonically normalized Goldstone bosons. They transform under adjacent gauge group sites exactly like a link does in lattice gauge theory. And therefore, this picture is just a discretized fifth dimension. It's just exactly what you'd write down if you just took lattice gauge theory when only put the fifth dimension on a lattice. It's important to notice that this is not fundamentally a lattice. There's really some ultraviolet physics which is giving you these Goldstone bosons. But at low energies, it looks like a discretized fifth dimension. The link fields Higgs these n copies of the gauge symmetry down to the diagonal subgroup. N minus 1 gauge bosons are massive. In any given example, you can compute their spectrum. And what you get is a spectrum that looks just like a Kaluza-Klein spectrum near the bottom of the tower. And near the top, you see the effects of the discretization. So at low energies, the theory just looks like a continuum 5-dimensional theory. And we have a picture that looks like this. Beneath the mass of the lightest one of these massive W bosons, which we interpreted as some effect of 1 over R, the theory looks 4-dimensional. In some intermediate regime, it looks 5-dimensional. And then in the ultraviolet, it looks 4-dimensional again. Okay, and there's some very simple relationship that we can make between the parameters of the 4-dimensional and higher dimensional theory. So this is what we call dimensional deconstruction. Okay, so that's just a very simple observation. But now I want to tell you some things that you can do with it. Depending on how I do for time, I hope to get through most of these. So one direction that you can take is, now that you've realized that these higher dimensional ingredients aren't particularly special to higher dimensions, you can go and think about mechanisms that you thought were intrinsically higher dimensional and just translate them into 4-dimensional language. Okay? So there are many, many examples of things that you can do here. I think an interesting one for this audience would be to go back and think about some of the higher dimensional mechanisms for circumventing problems in SUSY GUTS in completely 4-dimensional language. Another thing you can do is just use higher dimensions as a vague inspiration, and instead take this sort of more general notion of locality as a guide to build new kinds of completely 4-dimensional models that we hadn't thought about doing before. And this has been, at least to me, surprisingly fruitful. One of the things it's yielded is a qualitatively new way of stabilizing the Electroweak scale with a light Higgs and weakly coupled physics at TeV energies, but without any supersymmetry. So that's something I'd like to talk about. Then there's obvious connections to string theory. Of course, quiver diagrams come up all over the place. The simple observation that I made before can be used both in one direction to build higher dimensional theories out of 4-dimensional field theories and give some definition of 2, 0 theory and little string theory in terms of 4-dimensional superconformal field theories. And in another direction, to go to starting from lower dimensional theories, build 4-dimensional theories, and in this way, there seems to be a very promising hope that you can actually figure out how to put 4-dimensional supersymmetry on a lattice, which has been an outstanding problem for lattice gauge theory for a very long time. Okay. So first, higher dimensional to 4-dimensional mechanisms. By the early 80s, it was clear that supersymmetric GUTS had some terrific properties. They explained the standard model quantum numbers and gauge coupling unifications, but they also had some problems. Doublet, triplet splitting, bad relationships between Yukawa couplings, and so on. And then in the mid-80s, string theory and its extra dimensions came along and offered very interesting, novel, new ways of dealing with these problems, getting rid of the bad things while keeping the good things by using things like discrete Wilson line, symmetry breaking, and Calabi-Yau compactifications, projecting out unwanted state using orbifolds, and so on. Okay, now a lot of these mechanisms have cousins in extremely simple little 4-dimensional models with just 2 gauge group factors. So for example, the first mechanism has been understood in this four-dimensional way by a number of people. What I want to talk about just very briefly, just as a very simple illustration, is the second mechanism, projecting out things with orbifolds. Okay? So something that you typically like doing is breaking an SU5 gut by an orbifold and projecting out the triplets and keeping the doublets. Now what does that look like in this language? You have some chain that looks like this. There's a large sequence of middle sites, which are SU5, and two endpoint sites, which are SU3 cross SU2 cross U1. This is just an S1 mod Z2 orbifold deconstructed. Now, it's not a real grand unified theory, because there are these 3-2-1 factors at the ends. And I can have, for example, the standard model fermions be charged under the SU5, so the Higgs doublets only be charged under the last 3-2-1. It's not a real gut, but it has all the good features of a gut. In particular, the gauge coupling unification is preserved because this Higgs is Higgs down to the diagonal standard model subgroup, and the diagonal standard model subgroup's gauge coupling is dominated by these n group factors in the middle, which are unified. Okay. The standard model quantum numbers work out fine, but there's no doublet triplet splitting in this theory problem because there's simply no triplets. There's no reason for them to be any. The Higgses are charged into the 3-2-1 site. Now you can do something even simpler than this. We just have a theory with two sites. One of them be 3-2-1, and the other one be a weak SU5, with the 3-2-1 site being strong. This also has the feature that instead of using an n over G5 squared, this is just weak, that's strong, and again, it dominates. Okay, so this is just a very simple two-site model, which has all the good features of guts and very few of the bad ones. And you can use the same idea with just a different group theory and motivation as David E. Kaplan and Salva Simopoulos have done to talk about Electroweak unification near the TeV scale. Exactly the same story. Now you just reverse where the various fields live. Imagine you have, you're trying to embed SU2 cross U1 into a unified SU3 group. Let's just put the standard model fermions to be charged under SU2 cross U1, which is fine. They're not easy to embed into SU3. But have the Higgs be charged under the SU3 unification group. Same story. At low energies, the couplings are dominantly satisfy the SU3 relations. The Higgs comes out of a triplet of SU3, and this theory predicts at tree level that the sine squared theta for the Weinberg angle is 0.25. It's very close to the experimental value of 0.23. So you can have a picture where instead of having sine squared theta start at 3/8 and run down a long way to get the values today, you start with sine squared theta as 0.25 and run down just an order of magnitude to get the right value today. Okay. And it's a fairly natural group theory, essentially the same idea. Anyway, just two simple examples of how little two-site models capture a lot of this physics. That's, I guess, the slightly surprising thing is that it's definitely not surprising that you can discretize some higher dimensional idea. What's a little bit interesting is that often the essential features survive even for incredibly coarse discretizations of just two sites. Okay. So the second thing I wanted to talk about is the relationship of some of these ideas to string theory. Let me motivate it by saying that what I said at the beginning is that deconstruction provides an ultraviolet completion to higher dimensional gauge theories. But these higher dimensional gauge theories are discretized in the infrared. You can ask, is it possible to somehow send this effective lattice spacing to 0 while keeping the theory coupled? And if you just take some generic theory, the answer is no. It's very easy to see that if you try to take the lattice spacing to 0 and keep the couplings fixed, you have to send the gauge couplings at the sites to infinity. Of course, that's a running gauge coupling evaluated at the vacuum expectation value of that field. And so if you do this, typically the theory just goes out of this phase and something different happens. But you might be able to do this if you have a superconformal field theory with a fixed line of couplings. So the easiest example is to just take an n equals 2 quiver like that. And now we're going to give these link fields VEVs, go out along the Higgs branch, and at least just try to take this limit as G goes to infinity, and the VEV goes to infinity, keeping both this coupling and the radius, this effective radius, fixed. It's easy to see that this theory approximately doubles its supersymmetries, even perturbatively. So if it's going to deconstruct anything, it has to be some consistent 5-dimensional theory with 16 supercharges. There are none. So the only thing it could be is 2,0 theory in 6 dimensions compactified on a circle with one of the radii interpreted as as G5 squared. And I think there are pretty solid arguments that that actually happens. So if you think about the string embedding, where we can get the where we can get this quiver diagram, we can get it from KD3 branes probing a C3 mod ZN orbifold. So here are the KD3 branes. I've gone out along the Higgs branch, so I've moved them away from the orbifold fixed point. And I can just look at the masses of these stretched strings between the 3 brane and its images. And it's just a trivial little piece of geometry to see that the mass squared goes like sine squared n pi over n, where n is the image that you went over by. And at small n, this just looks exactly like a Kaluza-Klein tower. So it looks like a Kaluza-Klein tower for F strings. It also looks like a Kaluza-Klein tower, however, for D strings. So the massive W's of this theory are the KK spectrum of the naive 5th dimension that we were deconstructing before. But there's also a tower of monopoles, which reveals a hidden magnetic dimension, which you need if this is going to turn into 2,0 theory. And you can make a simple argument that what we're trying to do is take a decoupling limit here where I've moved this guy away from the orbifold fixed point. I'm trying to take n to infinity. I'm trying to keep the mass of this first stretch string fixed, so that's this expression. The mass of the corresponding D string fixed, that's the second expression. And in this limit, it looks like this orbifold is turning into a cylinder. So you can think of this as an orbifold regularizing a small circle, small cylinder. Now as I try to take the decoupling limits, I send L string to 0, the circle collapses to 0 size. A better description is obtained by T-duality. When I T-dualize, the string coupling gets huge, so I grow the 11th dimension. I went from a D3 brane to a wrapped D4 brane to an M5 brane, and you can check that this M5 brane and the decoupling limit compactified on a torus with exactly those radii. So this is an argument that this is indeed 2,0 theory. So we appear to have deconstructed 2,0 theory. There are a number of subtleties that I haven't discussed having to do with decoupling of various moduli and U1 factors that, but I think it's all probably okay. It's good that the 6th dimension wasn't there in the quiver and was generated dynamically, because 2,0 theory is chiral, and it should be very hard to put a chiral theory on a lattice. We're not latticizing, but this should be taken, if it's right, as a definition of some discretized version of 2,0 theory. Okay. And just for the sake of time, I won't go through. Well, you can do exactly the same thing to get little string theory. You start off with a mesh now instead of a, you start off with an n equals 1 superconformal field theory on that orbifold, and you get a sort of identification that the W bosons are the KK modes of the little string, the monopoles are the winding modes, and S duality in the field theory is T duality in the little string theory. Okay, well, so that's in the direction of going to higher dimensions. You can start from lower dimensions and go up. You can start with D0 branes on a C3 mod Zn cubed orbifold. And the same set of arguments would argue that as you went out along the Higgs branch, that this should turn into n equals 4 super Yang mills in 4 dimensions. But this is some quantum mechanics, and so this is defining a quantum mechanical definition for n equals 4 super Yang mills. This is a Hamiltonian lattice for n equals 4 super Yang mills. This is progress, because it's been impossible so far to put any supersymmetric theory with scalars on any kind of lattice. The difficulty is that the lattice, as a regulator, just immediately generates relevant operators that destroy the supersymmetry. In contrast to what happens with Lorentz invariants, where if you have a hypercubically invariant, rotationally invariant lattice, the leading relevant operators just happen to be there are no relevant operators that are hypercubic invariant and are not Lorentz invariant. That just doesn't happen for supersymmetries. And people have been trying to put supersymmetry on the lattice for a long time. So how is this working? Well, it's working because this looks nothing like a normal lattice. This is what the quiver gauge theory looks like. And it's some crazy looking lattice. It's a BCC symmetric cubic lattice. And there are different kinds of link fields. Some are chiral superfields, some are Fermi superfields. This is a quantum mechanics theory with 2,0 supersymmetry. So there are these funny multiplets with fermions and just auxiliary scalars. And not only that, this is not a lattice where you calculate correlation functions in the ground state of the theory. You calculate correlation functions in an excited state that corresponds to moving the d0 branes away from the fixed point. Okay. And you have to make some argument that, that there's a sort of wave packet spreading time that's slow enough that you can measure the interesting correlation functions that you want to measure in the quantum mechanics. Well, the claim, which was made, I think, pretty solidly in a beautiful paper on Hep lattice a couple of weeks ago by David Kaplan and collaborators, is that in this theory, the combination of the residual supersymmetry that you have, together with the non-trivial crystal symmetries, and some appropriate limits that I don't have time to discuss, really guarantee that there are no relevant operators that break n equals 4. And so this would be an example of an equals 4 supersymmetric theory on a lattice. And so far it's only on a spatial lattice. To make things really practical, you need a space-time lattice, which I suppose you could do by starting with the instantons on some Zn to the 4th orbifold, and with one supercharge, but I have no idea what that means, so I haven't thought about that very much. Okay. So, in my last 5 minutes, I want to tell you about a completely different topic now, which is this generalized notion of locality and electroweak symmetry breaking. In the standard model, okay, there's a hierarchy problem. We expect there's new physics at the TeV scale. Precision electroweak data suggests that this physics is perturbative. It's weakly coupled. And there's a Folk theorem that if you have a light Higgs and perturbative TeV scale physics, it has to be low energy supersymmetry. And the Folk theorem goes something like this. You draw diagrams. How else could you cancel the quadratic divergence? Okay, so the Folk theorem is wrong. And there's an alternative possibility, which has been a really old dream for model builders, going back to 1974 and 5, when Howard Georgi and Bram Pais thought that the Higgs should be light because it's a pseudo-Goldstone boson. I mean, it's sort of conservative, but the pion is light because it's a pseudo-Goldstone boson. Nambu didn't have to invent supersymmetry. Okay? And it was resuscitated again around 10 years later, but it never worked for a variety of reasons, mainly because the Higgs doesn't look much like a pseudo-Goldstone boson. It has all these hard order 1 couplings to other things and to itself. Okay. But inspired by deconstruction and this generalized notion of locality, we have finally been able to realize this possibility in really fully realistic models. And the models are also just incredibly small. They have very few new parameters and very few new particles beyond the standard model. In fact, they're the smallest extensions in the standard model to date that say anything about stabilizing the weak scale. There's perturbative and calculable physics at the TeV scale, and quadratic divergences are canceled by partners of the same statistics rather than of opposite statistics. Although this is a bad way of talking, really they're canceled by some interesting pattern of symmetry breaking and spurious symmetry analysis, which I'm going to quickly talk about now. So the idea is very simple. Let's just go back to one of our chains and imagine that these link fields are Goldstone bosons again. So in this model, n-1 of these link fields are eaten in the Higgsing down to the diagonal subgroup, but there's one that's classically massless that in the higher dimensional picture would just correspond to the Wilson line wrapping around this 5th dimension. In this picture, it's just that sort of discrete version of the Wilson line. Very naively, you would expect there's one-loop quadratic divergences in this theory that give this pseudo-Goldstone boson a huge mass, but it can't be. And it can't be for this very reason of locality that I was telling you earlier. In the limit where you turn off any one of these gauge couplings, the mousse is cut. It's cut, and there's an enlarged global symmetry that ensures that this object is an exact Goldstone boson. If you don't have a circle, you can't make this guy. Okay? And in the limit where you take one of the gauge couplings 0, you cut it. So that means that in this theory, there can't be any quadratic divergences till n loops. And it's got to be proportional to this product. There are finite one-loop corrections. That's allowed because infrared physics doesn't have to be analytic in the couplings of the theory. But there's no quadratic divergences till n loops. And so you get an interesting hierarchy of scales where you get a scalar that's significantly lighter than it should be compared to the true ultraviolet cutoff of the theory. Remember, this is a nonlinear sigma model, which isn't a renormalizable theory, but nonetheless, the scalar doesn't go one loop factor beneath the cutoff. It goes significantly beneath that. So these light scalars we called little Higgses. Little because they're light. They're lighter than they should be. Now, there are a lot of things you have to have for a realistic theory. In particular, you necessarily have to go to two-dimensional versions of these mousses because you have to have quartic couplings between the Higgses in order to have realistic physics. So, for example, if you have a toroidal theory like this, it's very easy to show that you, in fact, generate a quartic potential between the fields in the x and y directions, providing you shade in faces. Shading in faces here means that you add to the Lagrangian plaquette-type interactions for every face that you shade in. Okay, and I'm nearly done. So, about a year ago, Andy Cohen and Howard Georgi and I built a realistic model along these lines. And in the past 6 months, 5 months or so, together with some other collaborators, we've been beating these things down to their simplest possible manifestations. So here's one. There's an entire Lagrangian, which gives you a realistic theory of electroweak symmetry breaking. You're not supposed to take anything away from this, other than that I can write it down in 2 lines. And there's an even smaller one, which works. It doesn't even have a mousse structure for reasons that I can't explain, based on a different sort of symmetry breaking pattern of an SU5 mod SO5 coset for the Goldstone bosons. And in this theory, there's even fewer parameters. And so a silly table, just to see what I mean by these theories being really economical, is to look at the theory, look at the number of real degrees of freedom that it has and the number of parameters that it has, and now look at extensions. So the standard model is 118 real degrees of freedom and 19 parameters. The supersymmetric standard model adds 126 new degrees of freedom and around 100 new parameters generically. So these 2 little models add this many degrees of freedom and really a tiny number of new parameters. And the reason is that you're really just focusing on the interactions that need to be dealt with. So they can be extremely small. Okay. Unfortunately, I didn't get a chance to explain the physics of what went into the construction of those models. Okay, so let me just conclude. 4-dimensional theories that have a site and link structure are remarkably rich. They generalize higher dimensional locality and gauge symmetry in fruitful ways. And I hope to convince you in this talk that just from one very simple, small circle of ideas, a number of nice things come out. Ultraviolet completions of higher dimensional gauge theories, relationships to string theory, and supersymmetry on a lattice, and really the first alternative to weak scale supersymmetry, which has a light Higgs and makes sense as a nice theory at the TeV scale. And let me just end by saying the obvious question is what to do about gravity, and can we make sense of pictures like this where we have many copies of diffeomorphism invariant on different sites, work on that is rather furiously right now in progress with Howard Georgi and Matthew Schwartz. Thanks a lot. Sorry for going over time.
Okay. Questions?
Little string theories have scale, the string scale, and Hagedorn spectrum with state. Can you see these properties in the 4-dimensional theory?
The fact that there's a scale you can see, and there's a very loose argument, not that there's a Hagedorn spectrum, but that but that the free energy should blow up above some scale. So in the 2, 0 theory case, the limit we take in the superconformal field theory is some Higgs Vev to infinity and some gauge coupling to infinity, so the theory has no scale. It turns out, just from the point of view of the field theory, what you want to do for this 2-dimensional mousse is keep the Higgs Vev fixed as you send the couplings to infinity in some way. So that sets a scale. So the theory has a scale in it. And if you just argue what is the scale at which superconformality is broken in this theory, and if you naively argue it's this Vev, then immediately above the Vev, the free energy scales like n to some power, and that n is diverging. Beneath that scale, it just looks like a weakly coupled 6-dimensional Yang mousse. So at least there's some very weak hint that there is some something bad happens as you cross. Something happens as you cross this scale. There's a similar thing in the 2, 0 theory for the k-cubed coefficient in the free energy. And there's, again, a sort of very effective field theory-esque argument for why you should get the k-cubed, which I could explain to you if you want.
Okay. Other questions? Fernando.
What is the simplest way to put these ideas to test, experimentally?
Oh, they sort of have the virtue of being sufficiently predictive that there's a very definite spectrum of particles that you need to see. So in that simplest theory, first of all, beneath the TeV scale, you just see the minimal standard model and nothing else. Just a light Higgs, absolutely nothing else. And then at the TeV scale, you see 1 fermion, 1 scalar, and 1 massive gauge boson. And they have very predictive couplings to each other and to standard model fields. So,
when you say at the TeV scale, how literal that is since the factor of 2 is so crucial.
Factor of 2 is very crucial. So in fact, this is, depending on how weak coupling factors go, this theory could be the ultimate nightmare for the LHC. Just from the point of view of naturalness, the only particle you'd need to see in this theory just to have, and to be completely natural, it's totally fine to have this fermion at 1 TeV. This new gauge boson on scalar could be significantly heavier. They don't have to be, but it's definitely possible that you might not see anything.
The fermion couldn't be seen at 1 TeV in practice?
A 1 TeV fermion, actually, even this one's a little bit tricky because it would have to be pair produced. And but it's probably 1 TeV is probably okay. 2 TeV is deadly. So there is a small point of physics here. It's not just numbers. I mean, in supersymmetry, there's no reason why the Higgs should be lighter than all the other superpartners. It's just one of n scalars in the theory. In these theories, there's an excellent reason why the Higgs should be the first of all the particles you see, because it's the lightest pseudo-Goldstone boson. And so, so there's really a reason for there to be a natural separation of scales.
Okay, I actually have one real quick question, which just needs a sort of yes or no answer. Are there fundamental scalars in the models that you presented towards the end?
It depends how you ultraviolet complete the theories. In the second class of theories that I was talking about, you can actually get the pattern of condensation you need from fermion condensation.
Okay.
So,
and still get quark and lepton masses?
That is, I think, now a technical problem rather than a deadly problem. Because in these theories, the scales are pushed up high enough that, that you can now be, there was no shortage of cleverness for building models that did this. The problem was always that they're immediately excluded by experiment, and in this case, they're not.
What would be the order of magnitude of the number of degrees of freedom and new parameters if you got the fermion masses without fundamental scalars?
I'm not sure about that. I just don't know. I personally haven't had a huge amount of experience building theories like this. But it's certainly true that theories with fundamental scalars are a lot easier to put in fermion masses. And you could imagine UV completing these theories into supersymmetric theories at 100 TeV, which are okay.
Okay. Well, we've been warned that if we don't show up in time for the buses, we don't get to go to dinner. So we should